Hi everyone, and welcome back to this series of electrical B7 exam. And in this exam, we will be basically solving questions that are related to power flow. Okay, so this is question number 3. I solved two questions before. One of the question, it was the pre-starting of the calculations, which is basically was about how to identify the three buses types, which is the swing bus, the PQ bus, and the PV bus. How to set the voltages and the angle at each of those buses. Then there was another question, and that question was basically to solve the nonlinear equations to find the solution, which is basically the voltages and the angles at each bus, then we can find the power flow. This question is to extract information once you found the power flow, as we will see here. So here it says that this is a question about a power system. Okay, it has 1, 2, 3, 4, 5 buses. We have three different voltage levels. The generators basically generate the voltage at 13.8 kilovolt. We have these two transformers to step up the voltage from 3.8 to 230 kilovolt. Then we have TR1 and TR2 to step the voltage from 230 to 500 kilovolt. We can see here at the buses how much power is flowing at the beginning of the line and at the end of the line as well. The first question says here, are there any operational problems with this configuration? And it says here, explain. Now, this question, you could see things that I didn't find. I don't have the answer for this question, but I identified two issues or two problems with this configuration. The first one is about TR2. The transformer rating, meaning the maximum power that you can go through the transformer, was 800 MVA. So this is your transformer rating. However, there is going through the transformer, so this is the power flow or the power that go through the transformer is 899 megawatt. So there is a very clear overload in this transformer. Now, overload in the transformer is really bad because that would exceed or will increase the temperature of the transformer, and this basically will lead to a deterioration of the insulation of the transformer. So overloading, especially such high overloading, which is around 12-13%, is shouldn't be there in the power system. Yes, sometimes we are forced to do that, but this has to be for a very short period of time. So this is the first issue. The second issue I found is in L3. Now, L3 here is a transmission line, okay? Now, we have 380, and here this is 387 because what is entering the bus is 587. The load is consuming 200 megawatts, so basically 387 at the beginning of the line, so line 3. At the end of the line is 380. So we have 7 megawatt power loss. Okay. Now, when you look to the other line, L2 basically we have here 589 power in, 587 power out. So we have only 2 megawatt power loss. Now, while line 2 has more power, around 60% more than line 3, it has lower losses. So that tells me that this line number 3, is not efficient. The losses is basically high, and that is not really good. So these are the two problems that I identify from the operation of this power system. Now, here it says, if this load flow were being used as a long-term planning, we said that the load flow can be utilized or can be used for the operation or can be used also for the long-term or even the short-term plan. So this is, we see these issues, we identify these issues. So we want to basically, if the money is no object, so basically the money is not an issue here, Identify 3 solutions that could be improve the power system and steady-state performance. Okay, so this is part B. So I can suggest this is an open-ended problem. So one thing clearly that for TR2, basically replace it with bigger transformer. So we can basically replace it with a bigger transformer, okay, to accommodate for this overload. Okay, number two, you can also reroute the power through TR2. Now TR2 900 or almost megawatt is to supply this load. Okay, so if we did not change the transformer, one thing that I can supply more power from this route, supply to this load. Now this is maybe not the best efficient way, but at least you will not overload the transformer, which is usually very, very expensive. Number three, we can upgrade the line 3. So we can upgrade the line. Upgrade the line how? Either we have bigger or larger cross-sectional area conductors. So we can replace the conductor. So the resistance is less. The reason we have high losses here because the resistance is basically relatively high. So we can increase the cross-section area. We can have more bundle, basically. Instead of having one conductor or two conductor or three, make it four. So we can increase the number of bundles. Now, if we do that, the tower, maybe you need to replace the tower as well. Or you can construct another line in parallel. So you can construct completely new lines. So you can split the power between these two lines. So these are the things that I was thinking of to improve the operation of this power system. Then in part C, what is the efficiency of TR1? So the efficiency of anything is P out over Pn. So TR1, the amount of power that goes to the transformer here is the 95 megawatt and the 500 megawatt. So this is your Pn. So your Pn is 500 plus 95. So this is the power that goes to the transformer. The output is this power. This is the amount, which is the 589, and this will give me 98.99%. A very typical, this is the typical efficiency of those power transformer between 98 to 99%. What is the total line losses? So this is part D. The total power loss, we have three lines. So the power loss of L1 plus the power loss of L2 plus the power loss of L3. L1, so we start with 96 here. We end up with 95 megawatt at the end. So it means we lost 1 megawatt here. Plus, for line 2, we started with 589. We end up by 587, so there is 2 megawatt. We calculated that before. Plus line 3, we have here 587 coming here. We have here 2 megawatt coming out of this as a load. Okay, so then we'll have here 387. Here we have 380. So line 3 will have 7 megawatt. So the total loss is 10 megawatt. So this is how we can deal with a post-processing type of question for the load flow problem.